Welcome back. Let's learn about space curves and vector-valued functions. Alright, so far in Calculus 3, we really haven't done any calculus, have we? Right? We haven't done any limits, derivatives, or integrals, or anything like that, but that's all about to change very soon. In order to talk about calculus in 3 dimensions, we first needed to familiarize ourselves with the 3D coordinate system, with vectors, with surfaces, and everything else that we have looked at so far in Calculus 3. And now that we have done those things, we can start to put them all together and get to the calculus of Calculus 3. And so our first step to get there will be to introduce the idea of what we call vector-valued functions, or the way that I'm going to refer to them in this video, vector functions. And essentially, vector functions are just an extension of parametric equations from 2 dimensions. Remember from Calculus 2 that we defined plane curves, or the path of motion of an object in 2 dimensions, using parametric equations. We defined both x and y, which make up our coordinate points in the xy plane. We defined those 2 values with expressions or functions in terms of a parameter, typically t, where those 2 functions have a common domain. Right? So we would have x equals some function in terms of t, and y equals some function in terms of t, where depending on that value of t, the parameter, we would get a specific pair of x and y coordinates, and ultimately a point. And together, all of those points would make a curve that we would call a plane curve. A curve in a plane that has an orientation or direction, right? In the case of the plane curve that I have right here, it starts at this point, we would call it the initial point, and then it heads in this direction until it gets to the terminal point, which is the point where the curve stops. Now, plane curves don't have to have an initial and terminal point, but many of them do if we restrict the domain of that parameter t. Okay? And usually we like to think of that parameter t as representing time, but that's not necessarily always the case. We can have negative values of t, which doesn't really make sense if you're talking about time, and so I just like to think of t, or the parameter, as representing the order of a series of points that make up a path of motion. Alright, so that's nothing new. We talked about plane curves and parametric equations in Calculus 2, but now what we want to do is connect this idea to vectors. Remember that in 2 dimensions we can define a vector like this. Let's call our vector r. If vector r is a vector in 2 dimensions, it will have both an x component and a y component. So we would write that like this. We'd have x times the standard unit vector I plus y times the standard unit vector j. This is how we represent a vector in 2 dimensions. In particular, a position vector, meaning a vector whose initial point is the origin, right? It starts at the origin, and the vector ends at a terminal point determined by the x and y components of the vector. All right, so essentially x and y give you the coordinates of the terminal point for the vector. But what if we didn't know what x and y were, but rather we know how to find x and y given a parameter t? Well, we can use our parametric equations that give us x and y in terms of a parameter t to represent a vector, meaning we can put those equations in for x and y and create a vector function, a vector whose components are determined by a parameter t. So here's what that would look like. Since we are now creating a function, we're not just going to write our vector like this anymore. We're going to have the vector r of that parameter t is equal to its components in terms of the parameter t. So for x, that would be f of t. So you would have f of t times I. And then for y, that would be g of t. You'd have g of t times j. Okay, or if you prefer the bracket notation, you could also write it like this. The vector function r of t is equal to f of t, comma, g of t, where those components are inside of those vector brackets. Okay, so for a value of t, we could plug that into our vector function and get out a position vector, a vector whose terminal point is given to us by the x and y components. So we could do that over and over again for more and more values of t, and all of the terminal points from those position vectors would create a plane curve. Okay, so for example, we could plug in a specific value of t into this vector function to get out a specific vector. So let's say we put in some value for t, t sub 0, right? If we plug in a value of t, t sub 0 into this function, we will get out a corresponding vector. And that vector will have a terminal point somewhere along the plane curve that is represented by the vector function. Okay, so that vector might look something like this. That would be the vector r of t sub 0, that specific value of t that we are working with here. The terminal point of that vector is along the plane curve, and then we might use another value of t, let's say t sub 1, and that would give us another vector that would point to another point along that plane curve. So that would be the vector r of t sub 1, and we can continue to do this for more and more values of t to fully form our plane curve. All right, I could draw another one that would go up here to this point on the plane curve. That would correspond to another specific value of t that in this case I'll just call t sub 2. So that would be the vector r of t sub 2. Okay, my point being, vector functions in 2 dimensions represent plane curves. They give us a set of vectors whose terminal points form a plane curve in 2D space. So any vector you get from a vector function at a specific value of t will point to where you are along the plane curve at that value of t. Okay, but now we can extend this idea into the third dimension. And to do that, we first want to start by introducing another parametric equation, right? In 3D space, we're not just working with x and y, we're also working with z. So we'll still have parametric equations of x equals f of t and y equals g of t, but now we also need a parametric equation for z. We need to define z in terms of the parameter t. So we'll just use another function in terms of t. I'll call it h of t. So we'll have z equals h of t. Okay, so those would be the 3 parametric equations that we would use when working in 3D space. And so very similar to what we did in 2 dimensions, remember how we define a position vector in 3D? They have an x, y, and z component, which means that our vector r, in this case, would look like this. We'd have x times I plus y times j, and then plus z times k, where k is a standard unit vector for the z direction. Just like j is a standard unit vector in the y direction, and I is a standard unit vector in the x direction. This is how we would represent a single vector in 3D space, where the x, y, and z components give us the x, y, and z coordinates of the terminal point for that position vector. But if we only know what those coordinates are equal to in terms of another variable, in this case a parameter t, then what we can do is create a vector function in 3D where each of the x, y, and z components are determined by a function in terms of that parameter. So in 3D, we would have r of t is equal to f of t times I plus g of t times j plus h of t times k. And of course, you could rewrite that using the bracket notation as well. You would just have your brackets and then f of t, g of t, followed by h of t. Okay, but regardless, what we have here is a vector function in 3D space that represents a set of vectors whose terminal points would create a curve. Now, in 2 dimensions, our resulting curve is a plane curve, or a curve in a plane, but in 3D space, our resulting curve is a space curve, or a curve in 3D space. And so this is the big idea of this lesson. A vector function is a parametrically defined function where the terminal points of the vectors trace a curve in 3D space, which we call space curves. Okay, and so your space curve might look something like this. It is a curve that you would trace throughout 3D space. It is not contained within a plane like plane curves. It weaves in and out of planes in 3D space and can represent paths of motion that we couldn't represent in 2 dimensions. Okay, and so this space curve would be created by all the terminal points of the vectors that we would get from a vector function. And so just like I did for our plane curve, if we were to take a look at a couple of vectors for specific values of the parameter t, you could see how this plane curve would be formed. If we started with a value of t, let's say t sub 0, and we plug that into our vector function, that would give us a vector whose terminal point would be along this curve. So that might look something like this. We would call that r of t sub 0, and then we might use another value of t, let's say t sub 1, and plugging that into our vector function would give us another vector whose terminal point would be along this curve. So it might look something like this. So that would be r of t sub 1. And by the way, just like with the 2D example, I'm not using every single value of t that exists for this plane curve. I'm trying to give you just an example of a couple of these vectors. Obviously, there would be a lot more in between these two because there's a lot more points here along this space curve. I'm just giving you a couple examples of these vectors, not all of the vectors that would exist for this space curve. But then we could look at another value of t, let's say t sub 2, and that might give us a position vector like this, whose terminal point is along the space curve. So that would be r of t sub 2. Okay, so once again, what I'm trying to get you to understand here is how these space curves and plane curves are formed by vector functions. Vector functions just represent a set of vectors whose terminal points create a curve. Now, just a couple more things to take a note of here. First, it's important to remember that vector functions create curves, not surfaces. However, the curves can travel along surfaces. And you'll see that when we look at how to sketch space curves. A lot of the times what we have to do to help us sketch them is first draw a surface that the curve travels along. All right, so the vector function itself does not represent a surface, it represents a curve, but that curve might be on a surface. And then the other thing I want to mention is that space curves do have an orientation or direction. Just like plane curves, if you remember when we talked about them in Calculus 2 and the little review we just did a little bit ago, there is an order to the points for a plane curve, and that is also true for a space curve. You can see I have the direction labeled on this space curve with these little arrows. We start here at this initial point and end over here at this terminal point. Okay, so the order in which you get the terminal points for those vectors from specific values of t determine the direction. Okay, so as you increase the value of t, you get the next vector, which gives you the next terminal point for the space curve or plane curve that tells you the direction in which the curve is oriented. All right, so because t sub 1 comes after t sub 0, and the terminal point that corresponds to the vector for that parameter is here, and the terminal point for the vector corresponding to t sub 0 is over here, then we know that the curve has to go in this direction. It has to start from the lower value of t and head over to the higher value of t. Okay, and I've said this before, but the way I like to think about it is that the vectors that you get from a vector function point to where you are along a curve at a specific value of t. And if you think of t as representing time, then you can think of it as the vector telling you where you are along the curve at a specific moment in time. So the more that time passes, the further along the curve you will be. All right, so that's our introduction to space curves and vector-valued functions. But now let's take a look at a quick example where we actually work with a vector function. For this example, we want to find the domain of the vector-valued function and evaluate it at t equals 3. And then our vector function r of t is equal to the natural log of t times I minus e to the power of t times j minus t times k. Okay, so what does this mean? What does it mean, find the domain of the vector-valued function? We'll worry about evaluating it later. Let's start with the domain. What that's referring to is the fact that the vector function is defined in terms of a parameter t, or a variable t, right? So the domain of that vector-valued function, or the values of t that we can use for the function, are dependent on the functions for each component, the x, y, and z components. Okay, each of those components have their own function. If you think back to that general form for a vector function, we had f of t times I plus g of t times j plus h of t times k. Those were three functions in terms of t, that parameter, that give us the x, y, and z components for our vectors. So each of those three functions are going to have their own domains, or set of t values for which they are defined. And if we're not given that, it might be of interest for us to determine it. What values of t are valid for us to work with for a specific vector function? And the way we determine that domain is by considering the domain of each of those three functions for those three components. What we're really looking for here is a common domain, the domain of t values that is common between those three functions. So before we go any further here, what I think we should do is identify those three functions. Let's start with the x component. We have the natural log of t times I. So we know that x equals the natural log of t. And then for the y component, we have negative e to the power of t. So y is equal to negative e to the power of t. And then for the z component, we have negative t. So z equals negative t. Okay, so now what we want to do is determine the domain for each of these three functions, and where those three domains intersect will be the common domain for those three functions, and that will be the domain of the vector function itself. All right, so let's start with the x component here. We just have the natural log of t. For what values of t is the natural log function defined? Well, you can't plug any negative values in for the natural log function, right? It's not defined for negative input values, and it's also not defined at 0. If you plug 0 into the natural log function, you will get an undefined value. So for this function, t must be greater than 0. Let's then look at our y component. We have negative e to the power of t. If you think about what values of t this function is defined for, it should be any value of t, right? It doesn't matter what we put in for the power of this exponential function, we're going to get a real number back. So in this case, our domain is any value of t, which we just represent with negative infinity to infinity. And then the same thing is going to be true for our z component. We have negative t. You can plug in any value of t you'd like there, you're going to get a defined value. Nothing will be undefined. So once again, our domain here is negative infinity to infinity. Okay, so now we've identified the domain of the three functions that make up the components of our vector valued function. Now what we have to figure out is where do they intersect? What are the common values of t that these three functions are defined for? And that's pretty easy to determine in this case. For both y and z, we can use any value of t, but for x, that's where we have a restriction. In particular, t has to be greater than 0. So that's good. We can just use all values of t that are greater than 0, and we will be able to find a vector from this vector function for those values of t. Okay, so anything greater than 0 is going to work just fine. So our final answer here is that our common domain is values of t greater than 0. Or if you like to use interval notation, another way that you could write this is like this. You'd have an open bracket, 0, comma, infinity, and then another open bracket. All right, so that is the domain for this vector function. As long as we work with values of t greater than 0, we are going to get real numbers back for the components of our vectors. There will be no undefined values, so that's good. The other thing that we want to do for this example is simply evaluate our vector function at t equals 3. And that's just as easy as it sounds. You just want to plug 3 in for each t in the vector function. So here's what that will look like. We'll have r of 3, because that's the value of t that we are working with here, is equal to the natural log of 3 times I minus e to the power of 3 times j minus 3 times k. And that's it. There's really nothing here for us to simplify. If you want, you could get the decimal values for the natural log of 3 and e to the power of 3, but I don't see why we need to do that here. I think it's nice to just keep those exact values. If you want, you could use bracket notation for your vector, so you could also write it like this. You could have bracket the natural log of 3, comma, negative e to the power of 3, comma, negative 3, and then the other bracket. Okay, so either way, both of those answers would be correct. You don't have to write both of them. I just gave you both options here so that you know both of them would be correct. Okay, so those are two things you want to know how to do with vector functions. You want to know how to look at each of the components, determine their domain, and where you have common values of t will be the common domain or the domain of the entire vector function. And then of course you just want to know that you can evaluate a vector function for a specific value of t to get a vector, right? This represents a specific vector for t equals 3, and so these components would give us the terminal point for that vector, and that point would be somewhere along the space curve represented by this vector function. Okay, so now that you are familiar with vector functions, we can now begin to talk about how we go about sketching plane curves and space curves given a vector function. And the general guidelines look like this. The first thing that you want to do when sketching a plane or space curve given a vector function is you want to identify the x, y, and z components. It seems like a trivial thing to do, but you want to do it. You want to know what's my x component, what's my y component, and what's my z component. They should all be in terms of t because you're looking at a vector function, but regardless, you want to identify those components. Once you've done that, then what you want to do is eliminate the parameter t to get a curve or surface equation using at least one component. Okay, and what that actually looks like in practice is going to depend on your vector function. So you'll see that in our example problems, but something that you do want to note is that when your vector function just has two components, you are clearly working with a plane curve. So you're going to want to sketch your curve on a plane. But then when your vector function has three components, you are working in 3D space. So you want to sketch your curve in 3D, and most likely that curve is going to be on a surface that you want to try to identify and sketch. So you're going to sketch a surface, and then you will sketch the space curve that travels along that surface. Okay, and when you do that, you want to try to identify a surface that you are familiar with and know how to sketch a graph of. All right, something like a cylinder or a very basic quadric surface, such as a cone or a paraboloid of some kind. All right, so whatever you do in this second step, when you eliminate the parameter t in the components of your vector function, when you have three components, you want to try to use at least one or two of them to get an equation of some type of surface that you know how to sketch. And once again, if you're not quite following that, don't worry, you will see what I'm talking about in our example problems. Okay, and then finally, the third step is to use values of t to find at least 2 points and determine the orientation or direction of the space curve or plane curve. Okay, and that's probably the easiest part. You just pick some nice values of t to plug into your vector function to give you some vectors whose terminal points you can then plot and determine the orientation of the plane or space curve. Okay, so those are the general guidelines, but what do they look like in practice? Well, let's take a look at our first example. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. First up, we want to sketch the curve represented by the vector valued function and label the orientation of the curve. And our vector function is r of t is equal to the square root of t times I plus the quantity 9 minus t times j. Okay. So the first thing that I notice about this vector function is that it only has two components, right? We have an x component and a y component, but no z component. The z component is completely missing, so we know that this vector function is going to represent a plane curve. A curve in a plane, in this case specifically the xy plane, because we have the x component and y component. And so we are just working in two dimensions here. That's very important for us to identify right away. Okay, if you have two components, you're working in two dimensions. If you have three components, you're working in three dimensions. So if you want to write that down, like I did here, be sure to do that. That will help make sure you are on the right track to sketching the curve. And since we are going to be sketching it in a plane, specifically the XY plane, feel free to also draw yourself a two-dimensional coordinate system. But then what we want to do here is start with those guidelines we just went over. The first thing we want to do is identify each of our components. Now we only have two of them here, so we only have to identify two components, but regardless, we should still write them down explicitly. We know that the square root of t is our x component, and 9 minus t is our y component, so let's write that down. We'll have x equals the square root of t, and y equals 9 minus t. Those are our parametric equations from our vector function. Now, something you might want to do here before we go any further is identify the domain of your parameter t, because that's going to help you determine where your plane curve starts, if it does have a starting point or initial point, and it will also help you determine where it ends, if it does end at a terminal point. So looking at our two components here, 9 minus t is not going to have any restrictions on t. You can plug any value of t you'd like into this expression, and you will get a defined output for y. But we can't say the same for x equals the square root of t. There is a restriction here on what values of t we can work with. Remember that we're only working with real numbers. We're not going to work with any imaginary numbers, so we can't take the square root of any negative values. So we know that our values of t for the x component should be greater than or equal to 0. All right, so we know that the domain here is t greater than or equal to 0. And that would also be the domain for the entire vector function, because that would be the intersection with the domain of the y component. We said any value of t goes for the y component, so this would be the intersection, given that we can only use positive values of t and 0 for the x component. Okay, so this is our common domain, and this actually tells us that we will have an initial point, specifically t equals 0 will be our first value of t, and then after that there will be no terminal point. The curve goes on forever because there is no upper bound. We can just keep picking bigger and bigger values of t to plug into the vector function. Okay, so we've identified our components, found the domain. Now let's talk about how we're actually going to sketch this curve, and to do that we need to eliminate the parameter using at least one or two of our parametric equations. Now, in this case, we only have two, so we're going to use both of them. But as you'll see, when we work with three components, we kind of have to pick two, and then we use the other equation for something different. But we'll get to that. We only have two equations here, so let's just eliminate the parameter. This is something that we learned how to do in Calculus 2. So if you need a refresher, feel free to go back to the lesson on plane curves and parametric equations. But typically what you want to do is try to solve for t in one of your two equations, and then just plug what t is equal to into the other equation. So in this case, we can solve for t pretty easily in the x equation by just squaring both sides of the equation. So that will give us x squared equals t. So if t equals x squared, we can plug that in for t right here, and we will have eliminated the parameter. So we'll have y equals 9 minus x squared. Okay, and so what we get here is an equation of a curve that we know how to sketch. It might be helpful if I rewrite it like this. We have y equals negative x squared plus 9. I just reordered the terms, and hopefully now you can see what we have here is a parabola, specifically a parabola that opens up in the negative y direction and has a y-intercept of 9. So let me quickly sketch that here. Let's say that this right here is y equals 9. So that would mean that this is x equals 3 and this is x equals negative 3. And then we can draw our parabola. But something to be aware of here is that this curve that we just found does not necessarily represent our plane curve. It's just the curve that our plane curve will be on, if that makes sense, right? Because y equals negative x squared plus 9 would give us an entire parabola, but we might not use that entire parabola based on the domain of our values of t. Okay, so to start, what I'm going to do is just draw a dotted line version of our parabola. Okay, so that might look something like this. That would be our parabola in this case. That is the curve that our plane curve is going to travel along. Whether or not we use the entire curve is going to depend on the points that we find using some values of t. And so that's our next step here. We have now eliminated the parameter, found the curve that will contain our plane curve. Now we just have to finalize our sketch by plotting a couple points that will actually be on the plane curve. All right, so for our points, typically what you want to do is pick values of t that will make at least one of your components equal to 0, because then it will be easy to plot, right? When you have at least one component that is 0, it makes your point much easier to plot. So we'll keep that in mind for our second point. I think for the first one, it's pretty obvious what we should start with. We should just use the initial point, or the first value of t, which in this case would be t equals 0, right? We can't pick anything below 0, so we know that the curve is going to start at 0. So that's what I'm going to start with. Let's look at t equals 0. If we plug t equals 0 into our vector function, that's going to give us a vector whose terminal point will be along the plane curve. So we'll have r of 0 is equal to 0i plus 9j. So this is the vector for t equals 0. it takes us to the point with an x-coordinate of 0 and a y-coordinate of 9. So that would just be this point right here. Okay, so I'll plot that point. That is where t equals 0. And then let's pick one more point. I think that's all we're going to need to determine the direction and shape of our plane curve. We're either going to go in this direction or we're going to go in this direction based on the values of t we have to pick from. I'm guessing it's going to go in the positive direction, but we can't be sure until we check. So let's plug in a nice value of t. Remember, we want one of our components to be equal to 0. So I'll pick 9 for our value of t, because then we'll have 9 minus 9 for the y component. So if we do t equals 9, we'll have r of 9 equals the square root of 9 times I plus 0j. Now, the square root of 9 is 3. I'll just write that here. That's 3. So really what we get here is a vector whose terminal point has the coordinates of 3, 0, an x-coordinate of 3, and a y-coordinate of 0. All right, that will take us to this point right here, because that's where I labeled x equals 3 to be. So I'll plot that point. That right there is t equals 9. And now you can pretty clearly see the plane curve that we're working with. If this is t equals 0 and this is t equals 9, then this is our initial point, and we'll be heading in this direction. Okay, so I'll connect our points and then draw that curve in that direction and draw a couple little arrows there to indicate the direction. And that's it. That would be our plane curve right there. If you want, you could also label t equals 0 as the initial point. You could put that there, IP for initial point. But other than that, we have now sketched the plane curve represented by this vector function. And so we're ready to look at another example. For this example, we once again want to sketch the curve represented by the vector valued function and label the orientation of the curve. And our vector function this time is r of t is equal to the quantity 2 plus t times I plus the quantity 1 minus t times j plus the quantity 4 minus 3t times k. All right, and so unlike our previous example, in this example, our vector function has 3 components. There's an x component, a y component, and a z component. So we are not working with a plane curve or a curve in a plane. We are working with a space curve, a curve in 3D space. Okay, so if you want to make a note of that, be sure to do that now. And if you want to, you can also get ready to sketch the curve by drawing yourself a 3D coordinate system. And so now what we want to do is identify and explicitly write out our x, y, and z components. Our x component is what is being multiplied by I, our y component is what is being multiplied by j, and our z component is what is being multiplied by k. So for this vector function, we have x equals 2 plus t, y equals 1 minus t, and z equals 4 minus 3t. Okay, and now once again, we probably want to determine the domain for our parameter t. And just by looking at these 3 parametric equations, they're all just linear expressions, so there's really nothing that we could plug in for t that would create an undefined value. All values of t are going to be valid to use for these parametric equations. So our domain would just be from negative infinity to positive infinity. All right, and so now we've identified our 3 components and the domain for t, and so we're ready to move on to the next step for sketching a space curve. But I'm actually going to stop us there, because if you look closely, what do we have here? What do these 3 parametric equations represent? They should look familiar because they look exactly like something that we have previously learned in Calculus 3. If you want to think about it a little bit and you don't want me to spoil the answer for you, feel free to pause the video, but I'm going to spoil it now. What we have here are the parametric equations for a line in 3D space, right? This is exactly the form of a set of parametric equations that represents a line in a 3D coordinate system. We looked at this in a previous lesson. You have x, y, and z equal to some linear expression where you have t raised to the first power. It might have a coefficient or it might not. It could just be 1. And then you also have a constant term. So our space curve in this example is not really a curve per se. It's more of just a line in 3D space, which is totally fine. We can still sketch that, but there's no need for us to eliminate the parameter. That would just be a waste of our time. You could get the symmetric equation for a line in 3D space, but we don't really need to do that here. We can find points on this line as it is and sketch the line from those points. All right, and we really only need 2 points. One of them we can get pretty quickly if you remember how to find a point from a set of parametric equations for a line in 3D space. It's as easy as just looking at the constants in the 3 parametric equations. All right, that will specifically give you the point when t equals 0, right? Because if t is 0 in each of these equations, you're just going to be left with 2 for x, 1 for y, and 4 for z. Okay, so what we have here, if we're going to plot some points, starting with t equals 0, if we were to plug that into our vector function, we would have r of 0, and that would equal 2i plus j, or 1j, plus 4k. Okay, so that's a vector with a terminal point of 2, 1, 4. So let's plot that in our 3D coordinate system here. Let's let this be x equals 2, this will be y equals 1, and then this will be z equals 4. We need to plot a point that has those 3 coordinates. Remember that what you do is first find the shadow point in the xy plane. So you want to draw lines parallel to the opposite axis from each coordinate. And then where they meet is the shadow point of our point, which would be right about here. And so then you want to draw a line parallel to the z-axis. And then you want to draw a line from the z-coordinate to that line that is parallel to the line that you would draw from the origin to the shadow point. So that would be a pretty steep diagonal line. So we'll draw something like this. Not great, but that gives us an idea of where our point would be. So I'll plot it right there. Okay, that's our point for t equals 0. That's not the initial point in this case because we can work with all values of t from negative infinity to infinity. We're not starting at 0, so that's not the initial point. That's just one specific point that we decided to plot. Now we can plot another. Typically, I recommend that you pick a value of t that will make one of your components equal to 0. And I see a pretty nice one here. If we just let t equal 1 for the y component, you'll get 0 because you'll have 1 minus 1. So that works out pretty nicely. If we look at t equals 1, our vector function evaluated at 1 will be equal to 3i plus 0j plus k, right? 2 plus 1 is 3, 1 minus 1 is 0, and 4 minus 3 times 1 is 4 minus 3, which is 1, so we just have k. All right, so this vector has a terminal point of 3, 0, 1, which we can plot in our 3D coordinate system. I'll say that x equals 3 is right here, and z equals 1 is right here. So we want to plot this point in the xz plane, right? There is no y coordinate, so we're in the xz plane. So just draw some lines parallel to the opposing axis. So from the z coordinate, we'll draw a line parallel to the x-axis, and from the x coordinate, we'll draw a line parallel to the z-axis. And those two lines meet right here. So that is our point where t equals 1. Okay, and that's all we need, right? This is a line in 3D space. I forgot to write that. This is a line. The whole thing represents a line in 3D space. So we're done. We have 2 points. All we have to do is draw a line between them, and that's good enough to represent our entire line. We just have to remember to also label the orientation. Okay, so I'll draw a line that crosses through those 2 points, just like that. And then I'll just quickly refill those points so it looks a little bit nicer. But then what we want to do is label the direction. And since this point is t equals 0 and this point is t equals 1, that means we're going from here to here. So our direction looks like this. Okay, there is no initial point or terminal point, so we don't need to write that here. But this would be an acceptable sketch of our space curve represented by this vector function. It turned out that it was just a line, which was pretty nice. All right, now when your space curve is a line, it's fairly straightforward how to sketch it in 3D space, but not all of your space curves will just be lines. You will actually have curves that travel along a surface where there is actual curvature. Okay, in this case, this line is just traveling along a plane in 3D space. It's not one of our coordinate planes like the xy plane, yz, or xz plane like we would have for plane curves. But this space curve, or more accurately, this line, travels along a plane, which is a type of surface in 3D space. But the majority of space curves are going to travel along surfaces that are a little bit more complicated than just a flat plane. So let's take a look at one more example where we will sketch a space curve that actually curves. All right, so for our last example, we want to sketch the curve represented by the vector valued function and label the orientation of the curve. And our vector function this time is r of t is equal to a vector with components of 2 cosine t, 2 sine t, and t. And then we're actually given the domain of t in this case. We know that t is greater than or equal to 0, but less than or equal to 2 pi. Okay, so that's one less thing that we have to do. We don't have to determine our domain. The domain has been given to us, and it is restricted. The values of t do not go on to infinity and negative infinity. We're going to be staying in between two specific values of t. Okay, so in this case, there will be an initial point and there will be a terminal point for our curve. Now, do we have a plane curve or a space curve? I sort of already mentioned it, but since we have three components here, we have an x, y, and z component for our vector, it's very clear that we are working with a space curve. We are drawing a curve in 3D space. All right, so if you want to make a note of that, feel free to do it. And then also prepare to sketch the space curve by drawing yourself a 3D coordinate system. Mine will look like this. You'll see that I have the xy plane a little bit lower along the z-axis than I usually do. And that's because if you're looking at the values of t that we're working with, it's only between 0 and 2 pi, and the z component for all of our vectors is just t. So t is never going to be below 0, so we're never going to have a point with a negative z coordinate. All right, so we're always going to be either on or above the xy plane in our 3D coordinate system, so I just adjust it accordingly so that we have more space to work with in the positive z direction, since that's where all of our points are going to be. All right, so we know we're working with a space curve, but before we can sketch it, we do need to identify our components. We have the x, y, and z right here, but let's write them out explicitly. We know that x equals 2 times cosine t, y equals 2 times sine t, and z equals t. Okay, and so now this is where things might get a little bit tricky. We've identified our three components. Now what we have to do to help us sketch the space curve is eliminate the parameter. And we do have to do that in this case, unlike in our last example, because this does not represent a line, right? We don't know what these three parametric equations represent. We don't know the type of curve that we're working with here. So we are going to need to eliminate the parameter using at least two of our components. And so what are we going to do in this specific example? How are we going to eliminate the parameter using at least one or two components? Well, x and y work very nicely together because x is 2 times cosine t and y is 2 times sine t. Whenever you have two components where one involves cosine and the other involves sine, and both of them are just to the first power, you can very easily convert that to be in the form of the equation of a circle. Or even if the coefficients did not match, you could get the equation of an ellipse, right? This is something that we did in Calculus 2 when we introduced parametric equations and eliminating the parameter. Whenever you had sine and cosine, what you would do is use their Pythagorean identity to create the equation of a circle, or sometimes an ellipse. Okay, remember that cosine squared t plus sine squared t, or any variable that you put in for cosine or sine, as long as it's the same variable, if you add both of them squared, that's equal to 1. So if we solve for sine t in this equation and solve for cosine t in this equation, we can plug them in, square them, and we'll have the equation of a circle. All right, so for our x component, if we divide both sides by 2, we'll have x divided by 2 equals cosine t. And then for the y component, if we divide both sides by 2, we'll have y divided by 2 is equal to sine t. Okay, so cosine t is x divided by 2, and sine t is y divided by 2. We can plug that into this equation, and we will get x squared divided by 4 plus y squared divided by 4 equals 1. Now, if you multiply both sides of the equation by 4, you get this. You'll have x squared plus y squared equals 4, which is the equation of a circle, at least when we're working in 2 dimensions. But we're not working in 2 dimensions, are we? We're working in 3 dimensions. So yes, this is the equation of a circle, but in 3 dimensions, it is the equation of a cylinder, specifically a cylinder with a trace of a circle that has a radius of 2, which is the square root of 4, and that trace would be in the xy plane and projected along the z-axis. Right? Remember that when you work with equations in 3D space, when you only have two variables in that equation, it is the equation of a cylinder. And the missing variable tells you the axis for which the cylinder is directed along. Okay, so what we're going to do here is sketch a cylinder in this 3D coordinate system. And that's going to seem weird at first because aren't we trying to sketch a curve, right? We're trying to sketch a space curve here. Why are we drawing a cylinder? Well, remember what we talked about earlier with the general guidelines for sketching these space curves. Sometimes you're going to have to find a surface for which the space curve will travel along. And that's what we have found in this case. This surface, or this cylinder, is going to contain the space curve. The space curve is going to travel along the shape of this cylinder. And you'll see that as we finalize this sketch. But for now, let's draw the cylinder. It does have a trace of a circle in the xy plane, and that circle has a radius of 2. So let this be x equals 2, y equals 2, x equals negative 2, and y equals negative 2. And so our trace of a circle in the xy plane will look something like this. And then what we want to do to finalize the sketch of the cylinder is draw some lines parallel to the direction axis, which in this case would be the z-axis because that's the missing variable from our equation. So I'll draw some parallel lines here, followed by a projection of that trace. Okay, that's good enough. It's not perfect, but that is going to help us sketch the space curve. All right, so what we have here is a cylinder for which our space curve is going to travel along. The cylinder itself is not the space curve, it's just going to contain it. All right, just like with our example with a plane curve, we first drew the parabola that would contain the plane curve. It's the same idea here. We are drawing a surface that is going to contain the space curve. Now, you might be saying to yourself, well, wait a minute, we didn't use that z component at all. What about the z component? What is going on here? Well, I want you to think about it like this. From the x and y components, we found a surface that the points of our curve are going to be contained within, but then it will be the z component's job to determine the actual shape of that curve within that surface, okay, or within that cylinder. Because if z was just equal to some constant value, let's say z was equal to 0, well, we would just have a curve in the xy plane, right? We would never go above the xy plane. Our space curve would just be the trace of this circle in the xy plane. Or if it was a constant other than 0, we would just have a circle within the cylinder at that value of z. But because z is not just a constant value, it's equal to t, the z-coordinate of the points that make up the space curve are going to be dependent on the value of that parameter. So that will actually dictate the shape of our curve. It's not just going to be a circle, it's going to create some other shape as it travels through this cylinder. Okay, so I hope that helps you make a little bit more sense of what we're doing here. It does seem a little bit weird that we are eliminating the parameter in only 2 equations and just forgetting about the third one, but we're really not forgetting about it. We're still going to take it into account when we plot our points. Speaking of which, let's do that now. What we want to do is find some points for our space curve by plugging in some values of t into our vector function. So let's start with the first value of t equals 0. That's going to give us our initial point where the space curve starts, since our values of t are restricted, and then eventually we will get to the terminal point as well, but I am going to pick some values of t in between 0 and 2 pi to sort of bridge the gap. But let's start with t equals 0. What we want to do is plug t equals 0 into our vector function. So we'll have r of 0 equals a vector with these components where we plug 0 in for t. So cosine of 0 is 1, so you'll have 2 times 1. Sine of 0 is 0, so that will be 0. And then t equals 0 is just 0. So our vector is 2, 0, 0. So the terminal point of 2, 0, 0 for that position vector gives us our initial point for the space curve. So let's plot that. We're just going to be at an x value of 2, so that will be right here. So we'll plot our initial point. That is for t equals 0, and that is the initial point. So I'll write IP. Okay, so then, before we look at the terminal point of 2 pi, we will need to look at a couple more values. I'm just going to pick some nice convenient values of t that we know how to evaluate easily in cosine and sine. So I'm going to look at t equals pi divided by 2, t equals pi, and t equals 3 pi divided by 2. And then, of course, we'll look at t equals 2 pi. Okay? So that will give us enough points to get an idea of the shape of this space curve. It's not like a line in 3D space where you really only need 2 points to get an idea of the picture. In this case, we're going to need a couple more because it's not just a line, there's going to be some curvature here. So let's start with pi divided by 2. We want to plug that into our vector function. Cosine of pi divided by 2 is 0, so this whole component will be 0. Sine of pi divided by 2 is 1, so we'll have 2 times 1, which is 2, and then t is just pi divided by 2. So we'll have 0, 2, pi divided by 2, and so let's plot the terminal point of that vector. The z-coordinate is pi divided by 2, so I'm going to label that on my z-axis here. In fact, all of our z-coordinates are just going to be based on the values of t that we pick, since z just equals t. So let me label all of those. We'll let this be pi divided by 2, this will be pi, this will be 3 pi divided by 2, and that will be 2 pi. Okay, so if we have a y-coordinate of 2 and a z-coordinate of pi divided by 2, that will take us to right here on our cylinder. So we'll plot a point right here, okay? We're at the height of pi divided by 2 and a y-coordinate of 2. So that would be our point where t equals pi divided by 2. Now next up we have t equals pi. If we plug that into our vector function, cosine of pi is -1, so we'll have -2. Sine of pi is 0, so this is 0, and t will just be pi. So r of pi is equal to -2, 0, pi. So let's plot that. Our x-coordinate is -2, so we're going to be back here. And then our z-coordinate is pi, so we're going to be right here. Okay, you want to draw some lines parallel to the opposing axis, and that will give you that point, which would be along the cylinder. All right, that has to be true. We got this cylinder from the parametric equations from our vector function, so we know that all of the points must lie within that cylinder. Okay, but that is where t equals pi. And then let's move on to 3 pi divided by 2. Cosine of 3 pi divided by 2 is 0, so this will be 0. Sine of 3 pi divided by 2 is -1, so that will be -2. And then t will be 3 pi divided by 2. So r of 3 pi divided by 2 is equal to 0, -2, 3 pi divided by 2. And so let's plot that terminal point for that position vector. Our y-coordinate is -2, and our z-coordinate is 3 pi divided by 2, so that will take us up here. So I'll plot that point right there. That's where t equals 3 pi divided by 2. And then finally, let's do t equals 2 pi. Cosine of 2 pi is 1, so we have 2 times 1, which is 2. Sine of 2 pi is 0, so that component is 0, and then t will be 2 pi. So let's write that in here. R of 2 pi is equal to 2, 0, 2 pi. Okay, so the terminal point for that vector will be at an x-coordinate of 2 and a z-coordinate of 2 pi. So that will take us right here. So that is t equals 2 pi, which is also the terminal point, or TP. All right, so now we have all of our points. Now we just have to connect them in order. This was our first one at t equals 0. Then we have t equals pi divided by 2, t equals pi, t equals 3 pi divided by 2, and t equals 2 pi. So let's connect them. I'm going to use a different color here so you can see the curve and not get it confused with the cylinder. The cylinder is just helping us see the curvature of our curve. So we'll start at the initial point. We'll be curving up to t equals pi divided by 2. Then we're going to continue to curve up to t equals pi. Then we have to make our way over to t equals 3 pi divided by 2. So that will look like this. And then we need to curve back to t equals 2 pi. So that will look like that. Okay, and then of course we want to label the direction here, or the orientation. Since we started down here and made our way like this, then we want to point our arrows in that direction. Okay, you don't have to draw as many arrows as me. I just like to make it very clear which way the space curve is directed. All right, and so that's our space curve. It looks a little weird because we're drawing it on a 2D surface, but really if we were to go beyond t equals 2 pi, which of course we couldn't in this case because it is restricted, but if you were to go beyond that, you would continue to have this spiral that would go up along the cylinder that we sketched here. You could continue to project it further in the positive z direction and then draw more of that spiral, and you would essentially have what we would call a helix. Okay, so pretty cool that we have a way to represent that type of curve. That is what vector functions allow us to do. We can represent really cool curves in 3D space by independently defining the x, y, and z components with a parameter t. Okay, and so that is it for this example, and this was also the last example for this video. If you want to get some more practice working with vector-valued functions and sketching space curves, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.